And welcome back to my YouTube channel, and today's in this video we shall start with classification of elements and periodicity in properties. I'll make a playlist of videos, you can watch that video. So let's start. So why do we need to classify elements? So many times you would have heard that things has to need to be classified for because each and everything wouldn't be able to it's not sufficient to study about each and every property of every element. So we have classified elements regarding their properties, whose properties were similar were kept together. So in 1800 only 31 elements were there, and by 1865 there were 63 elements, and present we have 114 elements, and still scientists are trying to synthesize elements. Okay, so in your NCRT readers you can just underline the things which I have highlighted. The genesis of periodic classification, the first one was Johann Daubermeier. So he gave the trends, and he gave the idea of trends. In 1829 he gave triads, law of triads. Okay, where the concept was of atomic weights. So that atomic weight was like, suppose lithium, sodium and potassium are there. So they are in a group, they are corresponding in a group. Lithium corresponds to sodium, then potassium. So lithium atomic weight is 7, potassium atomic weight is 39. If you take out the average, that is 39 plus 7 by 2, you get 23, the middle atomic weight, the atomic weight of the middle element. Okay, then comes the next scientist, John Alexander Newlands. In 1865 he gave law of octaves, increasing order of their atomic weights. The concept was increasing order of atomic weights. The previous one was also about atomic weight. Here also it's increasing order of atomic weight. Eighth element, every eighth element is having the similar property of the first element, and it resembles the music, the sound, like it is sa, re, ga, ma, pa, da, ni, sa. Again we get the sa of the first one, the sa which is at the 8th position. Okay, so this is only true only for the elements up to calcium, remember. And he was awarded by Davy Medal in 1887 by the Royal Society in London. Like here you can see lithium, then beryllium, then boron, then carbon, then nitrogen, then oxygen, then fluorine, and again which is lithium. Below lithium we have sodium in the group. So sodium has the same properties as lithium, and therefore we keep them in a group. And at his time, during Newlands, when he discovered law of octaves, only 57 elements were discovered. Inert gases were not discovered. Okay. Then came the Mendeleev, Lothar Meyer. Mendeleev and Lothar Meyer worked together in 1869. Lothar Meyer said about atomic volume, he said about melting point and about boiling points. But we don't hear about his name, we mostly hear about Mendeleev's name. For the first time, periodic law was given by Mendeleev. It says that the properties of the elements are a periodic function of their atomic weights. Its atomic weight. If you see the first thing which was law of triads, that was also belonging to atomic weight. Then again, if you go for law of octaves, that was also for weight, atomic weight. Here also it's atomic weight. The old periodic law was on atomic weight. Everything till now was on atomic weight, but later on they changed to atomic number. Let's see. So properties of elements are periodic function of their atomic weights. Horizontal rows are known as periods. Again they are made subgroups like A and B. Vertical columns were groups, elements having similar properties. So there are 8 groups and 7 periods. 18 groups and 7 periods. A small correction as 18. He arranged them in increasing order of atomic weights. But if you see argon and potassium, they have to be kept like this, like 39 and 40. But first, then tellurium and iodine and cobalt and nickel are the defects. And anomalous pairs were also there present in his period. Then in some cases he ignored the order of atomic weights and he concentrated on the similar properties. Okay, so iodine was having lower atomic weight than tellurium in group 6. but still it was placed in group 7 along with fluorine. Iodine was placed with fluorine, chlorine, bromine, because of similarities in properties. Right now it's in group 6, but it was placed in group 7. It's not about group, it's about period. So tellurium was kept later and iodine was kept first in the group 6th element, but now it's in 7th. Like if you see, group 6 elements is oxygen, sulfur, selenium, tellurium. Okay, but if you see the 7th group, fluorine, chlorine, bromine, iodine. So here Te, that is tellurium, is first and iodine is second. But before, what Mendeleev did, he kept iodine first and tellurium second. And one more thing, what a drawback was, he left several gaps. For example, both gallium and germanium, they were unknown, but still he left gaps saying that there are some elements, and even he said the properties of that element, but he didn't discover those elements. So he left the gap under aluminium, he left the gap under silicon, naming it as Eka aluminium, which is gallium, and Eka silicon, which was germanium. Remember, this is very important. Gallium is nothing but Eka aluminium and germanium is nothing but Eka silicon. If you see modern periodic law and the present form of the periodic table, in 1913 Henry Moseley, he saw an X-ray spectra of the elements where under root nu, where nu is the frequency of X-rays emitted, while against the atomic number gave a straight line, whereas when under root nu, that is frequency, it gave, when it was against atomic mass, it gave line was in straight. So he made a conclusion that instead of using atomic mass, atomic number should be given more priority because it is giving a straight line for the graph when we are comparing it with frequency. So then we changed it to, the law was changed to atomic number, that is the physical and chemical properties of the elements are periodic functions of their atomic numbers. The periodic law revealed important analogies among the 94 naturally occurring elements. Neptunium and plutonium, like actinium and protoactinium, are also found in pitchblende and ore of uranium. That's not important, but still, just have an idea. Atomic number is equal to the nuclear charge, that is number of protons, and number of electrons in a neutral atom are also equal. A modern version, long form of the periodic table, similar outer electronic configurations arranged in vertical columns. Elements which were having similar outer electronic configuration were arranged in vertical columns named as groups or families. The full form of IUPAC, that is International Union of Pure and Applied Chemistry, gave the groups 1 to 18, replacing the notations A, 1A, 2A, 3A till 7, then 1B, 7 till 7B, and then 0. 0 is nothing but, 0 group elements are nothing but your noble gases which do not react with others and totally are inert. So there are 7 periods and 18 groups. Period number corresponds to the highest principal quantum number of the elements in the period. First period 2 elements, subsequent periods like the second period, the third period, the fourth, it is 8, 8, 18, 18 and 32. Okay. Then 14 elements of 6th and 7th period that are named as lanthanides and actinides are placed separately in the bottom, named as F block elements, if you know it. Then at the bottom you have this, like Glenn T. Seaborgs. He discovered plutonium in 1940. He discovered transuranium elements from 94 to 102. And he also reconfigured of the periodic table, like where should be actinides and lanthanides should be placed, that actinides should be placed below lanthanides. And in 1951 he got Nobel Prize, and element 106 is also named as Seaborgium in his honor. And in history, what happened was there was an element, like Americans said that they discovered and Soviet scientists said that they discovered, that is element 104. So Americans said that rutherfordium, then they kept the name as rutherfordium, and Soviet kept the name as kurchatovium. So IUPAC, the group of people, group of scientists, they gave a systematic nomenclature that from the atomic number, the numerical roots for 0 and numbers 1 to 9 were given. If you see the digits like 0, 1, 2, 3 to 9, for 0 it was nil, for 1 it was un, for 2 it was bi, for 3 it was tri, for 4 quad, 5 pent, 6 hex, 7 sept, 8 oct, 9 n. An abbreviation is given as NUBTQPHSOE. Okay. And yes, after assigning these numbers, these names and abbreviations, we need to add ium at the last, ium. And the IUPAC names for elements with Z, that is atomic number above 100, is given. Okay. And always remember that under root nu is directly proportional to Z, that is frequency, under root frequency is directly proportional to atomic number, not weight. So we know 7 rows are there that are periods left to right, and 18 columns from top to bottom known as groups. And now remember this in periods, first period is very short, second period is and third period are short. Second period elements are known as bridge elements, and third period elements are known as typical elements, which are short. 4 fifth elements are long. Sixth group elements are the longest. Sixth period elements are the longest. So sixth period is the longest because we have lanthanides and actinides which are present below in the F block. We have to count that also. There are 14 total. And seventh period is incomplete yet. In some books, you can see that physical and chemical properties of elements are periodic functions of their electronic configuration instead of atomic number as the modern periodic law. That is also correct because your atomic numbers can be written as electronic configurations. Remember this, that the highest value of n determines the period, that is quantum number, principal quantum number, and elements n period have same number of atomic orbitals, that is n square. Suppose this is a given 105 is the given atomic number. So 1 is nothing but un, we just now saw. 0 is nothing but nil. 5 is nothing but pent. So unnil pentium is the name which should be given by the IUPAC rules. Here you go with periodic table. Here I didn't kept H because H is in between. It neither follows these group properties, it neither follows that right group properties. It's in between because it follows both the group. That is why we study about hydrogen compounds separately as separate chapter. So the first two blocks are known as S block elements, the middle block is D block elements, and the last block has total of six groups. Okay. So that is known as P block, and the last one is lanthanides and actinides having 14 groups and 2 periods. Okay. So S block, alkali metals, alkaline earth metals, boron family, carbon family, nitrogens, you have oxygen family, you have fluorine family, that is halogens, and the last one is noble gases or inert gases or zero group elements. Then this is lanthanides and actinides, remember. So here are the lanthanides. If you could see what I was talking about, so this group is the longest group. The first one will be the H and helium, hydrogen and helium, which are the shortest. Lithium, these are lithium and sodium, that is second, and the third period is the short group. Fourth and fifth are the long group. Sixth is a very longest group because it contains these elements also. And actinides, the seventh period. I'm telling again in group, that is its period, and seventh period is incomplete yet. Like 104 is given, so 1 is un, 0 is nil, 4 is quad, and we add em, so unnil quadium. Okay, 120 means unbinilium. So this is it for today's video. Let's see in the next video. Till then, bye.